Hi, this is Sabir Ahmed. Welcome you again to the computational finite difference method. In this lecture, I'm gonna teach you how you can uh, solve one-dimensional differential equation using the finite difference approximation, and how you can write the code using MATLAB, and how we can visualize this one-dimensional equation. So for this example, I'm going to show you this equation, and I'm going to solve this equation, and I'm going to write this equation, and I'll teach you all about that. Okay, so this is the one-dimensional equation y double prime. That means the second derivative of x equal to e to the power x square, right? So how we can transform this equation to linear equation, and then to a matrix form, and then to get a solution or something like that. Okay, so I'm going to show all the procedure of that today. Okay, so let's go to find out the solution of that. Okay, how we can do that. Okay, let's make a ball pen, something like that. Yeah, so we are given the differential equation d square y equal to dx square equal to e to the power x square, right? So we have to what do we have to do? At first we have to transform this equation to a linear equation. So how we can do that? So we can do that, we have only a way to do that if we replace this differential operators as second derivative using the finite difference approximation, then we can write down this. So how we can approximate, or how we can replace this? We know the second derivative of this is equivalent to some finite difference approximation. So what is that? Okay, say write down this. Sorry, I'm going to write down another. Oh, okay. So I think I should write down here. Okay. So what is the differential equation? D square y equal to dx square equal to, so we know. Okay, let's define our domain first. Okay, I think it'd be better. So if we have domain something like that, say we have domain this and this. Okay, so say for example this is our domain 0 to L, and length is L. As it is a one-dimensional equation, so I'm going to show you in this perspective. Okay, so we have to discretize this at first. So for example, I'm going to discretize into 5 different elements. So 1, 2, say something like that. Okay, so 0, say this is a 1, say this is the 2, this is the 3, and this is the 4, something like that. Okay, so it didn't matter how many division, how many segments you want to divide or something into these parts. Okay, it doesn't matter at all, so it's still up to you. Okay, so these are domain, and we can these are domain. So in this domain we have to solve this equation. So let's transform this differential equation to linear equation using the finite difference approximation. So what is the finite approximation of the second derivative? Let's write down. uh, okay, so what is we know say x plus a. So we know the differential equation minus 2x, sorry, this should be the 2x plus x minus a divided by x square. So we can write down, so this should be equal to e to the power x square, right? Okay, so we can write down later here x plus a minus 2x plus x minus a equal to x square into e to the power x square. Okay, so what is the age? So x is the distance between two successive nodes. So if we have what is the if you have one 0 and it's the 1, the difference between the two successive nodes is the 1. So 1 is always constant in this case, in this domain. So h is always equal to 1. So in this case, so we have a is equal to 1, right? Okay, so these are general equation. So we have transformed our differential equation to linear equations, right? So we have to transform this linear equation to matrix form. Okay, before going to this, I am going to make you understand why we have done this. Okay, So we have discretized this or discretized this domain. That means our domain into 4 segments, but we have 5 nodes. Okay, 1, 2, 3, 4, and 5. We have 5 nodes, right? Change the color and so that it will be more visualizable to you. Okay, so we have these are number one, number this is number two. We have 4 nodes. Yeah, these are the nodes, and we have to solve we have to solve this we have to solve this equation. We have to solve this equation to every node. So we'll get these are prime equation: x plus ace minus x, get the arrow, x plus ace minus 2x plus x minus ace equal to x square into e to the power x square. So if you want to determine the solution, so we have 5 nodes, right? Yeah, we have 5 nodes here. So we'll have 5 number of equations. So we have 5 unknown values, right? So you have to solve this equation to every node, and we have 5 nodes, so we have 5 unknown values. So we will get the 5 unknown equations. So from these 5 equations, we'll get the 5 unknown values. So we know the number of unknown values should be the number of unknown number of equations, right? So otherwise we couldn't find out that. So we have to solve this equation to every node. Okay, then we'll get the number of unknown values for this domain. Okay, so how we can do that? So let's see. So if what does this equation tells us? This equation tells us, for example, 2x. So for example, we want to determine the value at this point, right? So what we need, if we want to determine the our solution at this point, then we must know the values of neighboring points. Say for example, x minus ace, that means we must know the value at this point, and definitely we must know x plus ace, that means these values, right? Equal, this equation should be the x square plus x square. So how we can transform these 5 equations to matrix form? So before going to this, I'm going to a simple example to make you understand how we can transform this equation to a matrix form or something like that, so that you can get understand. Okay, so it's very, I think you know all about that. Besides this, I'm going to make you understand, because I'm assuming that there are many students here who doesn't know all about that. Okay, so we have many techniques. For example, we have 4 equation or something. mm, Say we have equation x1 plus say 2x1 plus 3x square 3 sorry I'm sorry. So no, I think it should be gone. Yeah. So x1 plus 2x2 plus 3x3 equal to 0. So let's say we have our 4 equations, something like that. So 2x2 plus 5x3 equal to 0. We have another, say 3x3 plus 4x4 equal to 0. Say another, we have say uh, 2x3 plus uh, 4x1 4x, say for 4x1 equal to 0. Okay, fine, no problem. So from the system of equations, we have how many numbers of unknowns? We have x1, x2, xt, and x4. So we have 4 unknown points, so 4 unknown values to be determined, right? And we have 4 unknown equations. So this system of equation can be solved to find out, these 4 unknown values at point x1, x2, and x3 and x4, right? So this system of equation can be solved. Okay, so we have assured that. So how we can transform this equation? So at this equation we have x1 coefficient, x1 value, x2, xt, but not x4. So then what is the value of x4 here in this equation? In this equation we have the x4 value is 0, right? So we can write down this xt plus 0 or something like that. So we have unknown. Uh, so say for example, so what are the unknowns? So for example, x equal to, we know, x1, x2, xt, and x4. These are the unknown values that to be determined, right? Okay, so we can transform this. How we can transform? So we have four unknown values. So every equation must represents the four segments, okay, to be determined. So for the first unknown equation, so we can write down the coefficient of first equation. So what is the x1, what is the coefficient of x1 at this first equation? For the first equation we have coefficient is 1, then what is the 2, then 3, then a coefficient of x4 at this equation is 0, right? Okay, so for equation 2 we have coefficient is 0 x1, and we have x2 coefficient is 2, x3 coefficient is 5, and x4 coefficient is 0. So at equation 3, so we have the coefficient of x1 is 0, x2 is 0, x3 is 3, and x4 is 4, right? Okay, so and same time we have the at equation, yeah, we have coefficient 4, and we have coefficient of x equal to 0, x3 equal to 2, and x4 should be the also 0. So okay, so these the matrix coefficient matrix of these four unknown equations. Yeah, and we can write down the unknown values here. X1, this should be the x2, x3, and this should be the x4. So these are the unknown coefficient, and if we equal, this should be equal to the all the equation have zero values. So uh, we have the zero values, zero, the zero, zero, and zero. So we have four unknown values, and all the equation have zero. Yeah, right. Okay, that's fantastic. And we have transformed our system equation to matrix form. Then we can how we can solve this. Okay, so these are the unknown values. If we solve this matrix form, then definitely we can get the unknown values of x1, x2, x3, and x4. So we can, if we write down this, for example, if you write down this, for example, if you write down this this coefficient matrix, say for example this is the x, and this x unknown value, say for example this is the x equal to f, right? So we have to find out the value of x. We have to find out the value of x. How we can find out this? Okay, we have x equal to a inverse times f. Okay, so from this equation, these are the equations. So from this equation you can find out the value of x. So this is the general procedure how we can transform the system of linear equation to a matrix form so that we can get the unknown values easily. Okay, the same way we have to transform this equation to a matrix form. Then you have to solve this. Okay, so we have to transform this system of linear equations to ax equal to f. Okay, so what if we are given the boundary condition? For example, here if we are given, say for example at point 0 we are given, say x1 value is 1, and at this point the value of is, say for example, 3. Okay, so what would be the equation for this equation? Okay, so for this equation is for number grid point 1, grid point 2, grid point 3, and something like that. So what will be the equation at grid point 2? So we have grid point, say for example, mm, if we have five unknown nodes, so x0, x1, x2, x3, and x4, something like that, right? Okay, so what is our equation in this form? Okay, using this, so this should be here, should be the one, for example, what is that, yeah. So if it is not x naught, then x naught equal to the 1, x naught plus all the other values, x1 plus x2 plus x3 equal to 0. This should be the 1. So we can the coefficient of this matrix. So the x1, if this is the x1, then this 0 should be replaced by 1, because this is the 1, and all other values should be here 0. Other values should be the 0 and 0, and we want the x naught and x naught, and the previous value equal to 1. The same way we can find out for the for node 4. So how we can do that? So in this case we have to write down this, in this case it should be the x1 x0 should be 0, x1 should also be 0, x2 0, and x and x4 something like that, x4 to x3 equal to, okay, 3. What is the coefficient of 1? This coefficient of 1. So in this case this should be the 0 0 0, and this should be the 1, and this should be replaced by this should be replaced by 3. Okay, so this is the way how we can transform our equation to matrix form. Okay, let's transform our system of equation, this system of equation, to a matrix form. So how we can do that? Okay, let's go to the next slide. So our equation is here, x minus a minus 2x plus x plus a is equal to so x plus h should be the x plus h x squared e to the power x squared, and our domain is something like that. Our domain, say for example, this is the 1, so this is the 2, this is the 3, this is the 4, say for example this is the 5, and this is 6, for example, something like that. Okay, so we have 5, we have 6, we have sorry, I've gotten a mistake. I think we should have to this down, this 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 and this, and this should be written, yep. So this is the 1, this is the 2, this is 3, 4, and 5, and something like that. Say the unknown value at this point is x0. Here the unknown value at this x1, unknown value at this point x2, unknown value at this point x3, unknown value at this point x4, and unknown value at this point is x5. Okay, so I didn't made a mistake, x1, x2, x3, x4, and x5. Yeah, something. So we have these unknown values to be determined, right? So how we can transform this equation, and let's define the distance between two successive nodes is same and is equal to 1. Okay, for example, this is the 1. Okay, so how we can do that? So a is equal to 1 or something like that. Okay, a is equal to 1 or something like that. Yeah, so it doesn't matter, so a is equal to 1. So this point is 1 2 3 4 and 5 6 something. So how we can transform this equation? So we have to say, for example, we are given some boundary conditions. So we know the value at this point is say for example is 1, x not equal to 1, and x5, this should be the say for example 3. Okay, so we are given the boundary condition at point 0, and at point 5 is 3 and 1 respectively, something like that. So let's transform this equation for every grid, nodal points. Okay, say x naught, so we know the x naught at this point, so we know the x naught. So x naught and all other values should be the 0, because we are given say x1 x2 x3 plus x4, sorry, this should be the 0 x4, and x5 should also be 0 equal to 1, we are given that, and 4.1 4.2. So if we write on this, so how we can do that? We must have to know the previous point. So we know the previous point 1, and minus 2 minus 2x minus 2x1. So we have to determine using this equation, right? Minus 2x naught. So from this, so previous point, so previous point is no 0, we know what is the coefficient of x naught, right? This should be the x naught. Okay, 1. So x naught minus 2x1, my x naught minus 2x1, then the x point is x2 plus 0 plus x3 0, x4 0, and x5 0 equal to h square. So what is the h square means? At this point we know h is equal to 1, and e to the power, at this point what is the value of x? So e to the power, so we know the 1, we know that a is equal to 1, and e to the power 1 square, right? E to the power 1 square. So this equation for nodal points 1, and this equation for second equation for nodal points 2, and I have to determine the third equation. So with third equation, in case of, so in this case of at point determine the 2, so we have to know these points and these points only, and all other points should be 0. Okay, so here the x naught is 0. We have to know x naught is 0 plus x1 minus 2x2 plus x3 plus x4. X4 is 0 and x5 is also 0, so is equal to e to the power 2 square. 2 square means we have what is the distance between this? 1 plus 1 equal to 2, so 2 square. Okay, at point 3, what is the value of point 3? Okay, so 0, same way you can write down x2, this should be the 0 plus x3 minus 2x4. Oh, sorry. This should be sorry. I've got a mistake. So yeah, the 0, right? Yeah. So transform this x not 0. So we're going to find out at point x3. So x2 minus 2x3 plus x4 plus x5 at point 0 equal to e to the power 3 square, right? Okay, 0 plus 0 plus 0 plus x3 minus 2x4 plus 0 equal to e to the power x, sorry, e to the power 4 square, yeah, and x.5. So what do you know x.5? So at x.5 we are given the boundary condition 3, so all the other points should be 0 plus 0 plus 0 plus 0, x0, x1, x2, x3, x4 should be the 0, and x5 equal to 3 because we are given. So at point x5, so we are given x5 equal to 3. So you've got the systemification for in case of our domain, right? So what if we have say thousands of or hundreds of grids, hundreds of nodal points? Then how we can write down this? We don't have to write all this equation. For making you understand and how to write down this and how to do this, so I'm doing this. Okay, so you don't have to write all the equation for all thousand nodes. Okay, for your convenience, I'm doing this in this case. Okay, so how we can transform this equation? Oh, my battery is going bad, so I'm coming back. I think we have to wait for a bit. uh, let's matter my battery. Okay, welcome back. Okay, so what I have to do right now, we have to transform the system of equation to matrix form. So how we can do that? Okay, let's go and let's do that. Okay, for x naught equals to the 1, sorry, x naught 1, another point should be 0 0 0 0, so 1 2 3. So we have 6 grids, 1 2 3 4 5, and should be the 0 in order to be the will have coefficient of x naught 1. This should be the minus 2 x naught here the at this point. So the value of coefficient of x1 at second equation is minus 2, so this should be the minus 2, right? And what is the value of x2 here? The value of x is 1, and all the other values should be 0 and 0, and this is the 1. Yep. So what is the third equation? 0, we can write down 1 minus 2 1 0 and 0 0 0 1 minus 2 0 and 0 2 3 4. We have number 1 0 0 0 1 minus 2 1. So and for the fifth equation, all should be the 0 except the 0 0 and 1. So this is the coefficient matrix, and this is the coefficient matrix or something like that. Yeah. I'm good. This is the coefficient matrix of the system. So we have the unknown values of x naught, x1, x2, x3, x4, x5. And what is the load vector here? The load vector, we have applied all the boundary conditions. So this should be the 1, this should be the e to the power 1 square, and this should be the e to the power 2 square, and this should be the e to the power 3 square, and e to the power 4 square, and 3. Okay, so if we solve this equation, I'm sure we can get this. So for example, if we write this a, and if we write this x, then definitely we'll get the value of x. So if we solve x, how we can a prime a prime multiplies by f. So we can solve this equation. Okay, I hope you have understood how we can transform our differential equation to linear equations, and then linear equations to matrix transformation, and we have to solve this equation so that we can get the solution at our domain. Okay, now times to transform this matrix or transform all these things to MATLAB code so that we can visualize and we can write a code, something like that. Okay, let's go to the MATLAB. Okay, MATLAB part. So how we can do that? Okay, so before going to MATLAB, I'm going to make you understand. So what are the process to write down the code? Okay, so at first I'm going to write something. Say number one. So we have to discretize the domain. This I don't know why my writing discretize the I don't know why it is doing like that. At first we have to discretize the domain. দুই number হচ্ছে generate generate matrix. For we have to at first generate matrix A, X, and F. All should be the zero matrix. Then we have to put our values, coefficient values for a particular domain. You know where to put this value. Okay, and number 3, apply boundary condition. Apply BC boundary condition. And number 4, then solution. And number 5, plot and visualize. Plot and visualize. Okay. So these are the general steps. So at first we have to discretize our domain. That means we have the define our physical properties. Then we have to define our numerical properties. How many segments and how many nodes and how many elements do you want to have in our domain. Then we have a generate matrix. Then you have to put the values of coefficient values to that matrix. Then we have to apply boundary conditions since for something like that boundary condition. Then we have to solve this matrix. Then we have to plot and visualize all those things. Okay, so these are the general procedure how to uh, write a code in MATLAB, or it doesn't matter. We have chosen this platform here because there's a lot of functions and a lot of things here available. In this case, if you want, if you can write code in other platforms as well, for example C#, C++, Java, Fortran, whatever, and wherever you want, you can do that. We have chosen the MATLAB because it's very much convenient, user friendly, and we have a lot of built-in functions, so we do not have to write this code. Okay, that's fantastic. Okay, let's go to the MATLAB because I have some codes. I have written some code for you so that I don't have to write code right now, and I'm going to make you understand what I have written over there. Okay, yeah, that's fantastic. Let's go to the MATLAB. Arrow. Okay, and show. Yeah, okay. Yeah, let's go to the MATLAB, and I have some code here, and these are solution plotting. And okay, so these are MATLAB code. So before writing this code, I assume that you do have some basic and primary knowledge of MATLAB and how you can write those things, and I'm sure you do know all about that. So if you do not have any previous experience writing code, then I do recommend to go to my website www Submit Foundation slash www.youtube.com/user/Submit Foundation. Okay, so I'm writing here. I'm writing here where to go. Same thing, www.youtube.com/user/submit foundation. And this is the website where I have put all my lectures there, so you can find out the introduction to basic MATLAB code. So if you do this and if you come back here, then I'm sure you'll find it more convenient and you'll find more better than you're experiencing right now. Okay. Okay. So I assume you have good knowledge of MATLAB writing code or something like that. Okay. So this is a MATLAB and I have written some codes in advance so that I can make you understand in fastly and I can make you understand all the code appropriately and accurately. Okay. So property determination, physical properties. Say for example, we have our domain whose length is 1 meter, something like that. Uh, in meter or something, in meter or kilometer, it doesn't matter. So it's really up to you. In meter. Yep. So you have numerical properties as well. So we want to discretize our domain. That means in 1 meter. So I have another things to make you understand. So it'll be better. Yeah. So we divided our domain into 5 equal segments. We divided our domain here into 5 equal segments. Okay. So yeah. So 5 equal segments and P, then we have divided, we want our domain to be divided into 5 equal segments. So number of elements and number of nodes to be the 5, and so we divided using the another MATLAB function. It's called the linearly spaced. So we want to divide it from 0 to L. So how many numbers in nx? So if we have, say for example, this is 0, so L equal to 1, so we want this domain to be divided into 5 equal number of segments. So say for example this 1 2 3 4 5. So we do not have equal space, but this function will do this the exact same. Okay, so what is the distance between two successive nodes? Dx, so equal to Pnx. So Pnx means we'll get the vector P, right? Because we'll get the nodal values, five nodal values at point. So Pnx means 5. So what is the number of 5? 1, and then minus Pnx minus 1. So what is the if we can find out the difference between these and these, then we can find out the difference the two successive nodes. Okay, so dx equal to the difference between the two successive nodes. Okay, so this is our physical property determination. So physical property determination consists of two parts. Number one, physical properties. Number two, the numerical properties. Okay, this is the numerical properties and this is the physical properties. Okay, right now we are interested to matrix generation. So we have a, right, a and array. So we have seen that zero is a built-in function here in MATLAB that can be generated a matrix nx equal to the number of rows and number of columns. Okay, so we have number of rows equal to how many we have unknown values in this domain is 5, right? So we have number of columns and number of rows must be equal. So that's why we have generated a vector, because we have seen in my we have seen here that here we have number of rows and number of columns the same, because we have 1 2 3 4 5 6, we have 6 nodal points. So we have 1 0 1 number of rows 1 2 3 4 5 6, because we have 6 unknown values, 6 unknown equations and 6 unknown values. So we have 6 unknown columns. That's why I have selected. We have to generate a matrix having the same number of rows and same number of columns. Okay, yeah. So RS is right hand side. That means this one is the right hand side. So what do we know? Right hand side, we know the right hand side is x square into e to the power x square. Okay, so initially you have generated all the values should be 0. Initially we have all the values should be 0, right? RS is equal to, so yeah. Yep. So initially we have all this value had been 0. Okay. So this is the matrix generation, our required matrix, and we will get the other matrix. Okay. Coefficient matrix data collection. So how you can put this? Okay. For every equation, for I equal, this should be the -2, because at this equation of, if we go to the equation, and if we go to the something like that, the every equation, for example, this is the 1 1, this is the 1 1, right? In this matrix, this is the 1 1, this is the 2 2, these are 3 3, 4 4, 5 5, and something like that. So every diagonal element have -2, because if you see the equation, you will get this is the 2 2, right? This is the 2 2 -2, and the previous point is 1 and next point is 1. So every diagonal point is -2, and this previous point is 1 and next point is 1. So you have to write down same things. Every diagonal point is -2, and its previous point is 1, and its next point with a right 1. Okay, that's the thing. So we have put our we have got our coefficient matrix as well. Okay, now we have to apply the boundary condition. So what are the boundary condition? So we know the boundary condition. Now apply boundary condition to RSS and data input. RSS and data input. Okay. Okay. So what are the data? Because what are the data in case of our load vector? This is the force vector or load vector. It doesn't matter. So we have to put these values to our matrix RSS. So we have number of rows, n number of rows. That means in this case we have five, okay, and one column, so this should be something like that. Yeah. So every value should be, if equal to 1, then should be 0. So we have put the boundary condition at point 1 and at point nx equal to 0, and all other values should be dx squared. That means h squared. So we know that a is equal to dx here. Okay, into e to the power x square. So e to the power, that means y equal to px. Px means x square. X means in which nodal point we are here, right? So if we are from I equal to 1 to x, so we have domain 1 x0 to x5, right? We have x0 x5. So uh, so pi represents the distance from 0. So pi, it should be, say for example, is 1 to, if 1 is equal to 1, this, if nodal point is 1, that means it should be 0. If nodal point is nx, this should be the 0. In case of 2, 3, 4, this should be the something like that. Okay, so this is the boundary condition, and the RSS, the load vector, something like that. Yeah. So boundary condition for stiffness matrix. So we know the 1 1, the first elementary values x naught, the coefficient of x naught, we know the 1, and the last value x5, so coefficient value of x naught 5 1. Okay, so we have applied the boundary condition for stiffness matrix. Okay, then this should be the result equal to A inverse. In MATLAB, if we backslash, is determined by A inverse into RSS, right? So we have got this, and the plot P, we have got the P and D. P means or the distance. With distance, what is the value of that? So we have got the value D here. So that's the solution, and plotting and visualization. So great period. Okay. So I'm going to show this in debugging mode so that you can understand what's going on behind this code. Okay. So for debugging, I have put here uh, the thing. So I'm going to save and run first example, or something like that. Yeah. So if I press F11, then it will go step by step. Okay. You have to press always. Okay. Oh yeah. Okay, so if we right click cursor, L equal to 1 or domain is 1, n x equal to 5, and you will get the P equal to the nodal point. So we have 5 0 to 0 to 1. So we have divided this domain into equal 5 parts. So what is the nodal points? 0 0.25, 0 0.5, 0 0.75 and 1, right? Okay, so what is the plus dx? We calculated this. So if you take your cursor here, you will get the difference between two successive node is 0 0.25 and something like that, and we'll get another matrix. So we have got another matrix, this. So we have the 5 into 5 double, that means we have 5 rows and 5 columns. So is all the zero values, but we have to later we have to put our coefficient values in appropriate places. Okay, so F, F11, so we have write down here 5 into 1. So we have 5 into 1, that means we have already seen that in 5 into 1, right? So is the sorry, we have 1 2 3 4 5 6 into 1. So we have 6 rows but 1 column. In this case, in our case, we have 5 rows and 1 column. Okay, so coefficient matrix data collection. So how we can do that? Okay, let's go to this, and uh, uh, I equal to 2 is to because we don't have 2 is to n minus x. Why I put in the 2? Because we don't have 1, because um, for 1 and nx we will have boundary condition here, right? For 1 and nx we have boundary condition here, because that's why we avoided the 1 nodal values and nx nodal values. That's why we have written here from 2 to nx minus 1, right? Okay, that's another thing. So let's go to from at point nodal point 2, because if you look at here, uh, at equation 1 and at equation nx is fixed 1 and 1. So we know why it is 1, because all the other nodal values are 0 except this point. Okay, yeah. So yeah, so if we press up to nx minus 1, so next, so you've got the value of n. So let's see, let's uh, minus 1 minus 2 for equation 2, we have minus 2 at point x2 and x1 we know, and x3 at the same way we know all about that. Yeah, so apply the boundary condition to RSS and data input. So if we at nodal point 1 RSS, that means left hand side, that means force vector, load vector. So we know this value and this value. So in this case we have put 0 and 0, but in our example we have put here 1 and nx value is 0. Now that then all the simplification follow this. Okay, so this and this. So let's see what is the value of that. Yeah, 0 and 0. So first value is 0 and the last value is 0, and all other points calculated from this equation x square into e to the power x square, right? Okay, so apply the boundary condition for stiffness matrix. So what is that? A equal to 1, 1 equal to 1. So we know 1 and a equal to nx, and this stiffness matrix because we have calculated from 2 to n minus nx minus 1. So this nx minus 1. Okay, so we have got the RSS and A. So if we know the A inverse and RSS, then in MATLAB we can write down A inverse into A backslash into RSS. So we'll get our desired result D. Okay, so we have got the result D 0 because we know the 0 because we have applied the boundary condition at point 1 and at point nx. We know also the 0 because we have already, because these are prefixed and predetermined and we are given this condition. Okay, yeah. So now you have to plot this and you have to visualize this equation. So plot plot f12 and something like that, f12 sorry, f11 oh, so huge. Okay, we can press this this continue. So you've got this circle. So uh, So you have got our desired solution and this is a visualization. So at point 0, we have got zero, we fixed it, this should be 0, and at point 1 this should be fixed to 0, and we have identified this 2.25, 0.25 at point B, 0.5, 0.75. So we have got 3 values or something like that. Okay. Yeah, so this is the general procedure how to write code and how to make things. Okay, let's make a little change in a code so that we can visualize more better, right? You may ask, what if I change the our domain? So for example, if you want to put a 5 meter, okay, fine, no problem. And if you want this 5 meter to be divided into 50 equal segments, no problem, let's put 50. And code is the run first example. Yeah, so this is the desired solution and these are the equations. So we'll get the 50 nodal values and solution is something like that. Okay, so what if 50, our domain is 50 meter, and we want to divide our domain into 50 equal parts? No problem, go. And we do not see anything because we have some um, we have something that needs to be fixed, but we can do that. But in this case we may not have solution or something like that. So if we have, say for example, 10, we have solution something like that. Okay, so these are the general procedure how you can write code or how you can do that in MATLAB, and how you can transform a differential equation to linear equations, and then linear equation to matrix form, and how you can solve this matrix form in coding by coding in MATLAB or in C++ or in Fortran or something like that. This is general procedure same. So my basic objective is to make you understand how to write a differential equation into a linear form, linear algebraic form, and this transform this linear algebraic form to a matrix form, then find a solution and then write a code. Okay, so I hope you have got through this and you have understood all about that. So if you do not get through this, please write me. So please write me and I will be happy to answer you all. Thank you. I think you have understood. Thank you very much for your time and for this lecture. Okay, bye. I hope I will see you next lecture.